In early January 1998, the power grids of eastern Ontario, southern Quebec, northern New York, and portions of New England operated under design assumptions developed for regional winter conditions. These systems anticipated snow loading, periodic wind stress, and brief ice events lasting 6 to 12 hours. Transmission towers were engineered to specific load thresholds. Distribution lines carried standard winter capacity. Transportation networks functioned with routine winter maintenance protocols. Municipal infrastructure reflected expectations of manageable winter precipitation. The region had experienced ice storms before, but none that persisted across multiple consecutive days with continuous freezing rain deposition. The affected region extended from eastern Ontario through southern Quebec into northern New York, Vermont, New Hampshire, and Maine. This corridor lies at the confluence of Arctic air masses from the north and moist systems from the Gulf of Mexico and Atlantic Ocean. Winter weather typically involves cold fronts, snow events, and occasional freezing rain of limited duration. Power transmission infrastructure consisted of high-voltage towers supporting lines across rural and forested terrain, with distribution networks serving urban centers including Montreal, Ottawa, and surrounding municipalities. These systems were designed to Ontario Hydro and Hydro-Quebec engineering standards that accounted for ice accumulation of approximately 12 to 25 millimeters radial thickness on conductors. Transportation networks included Autoroute 20, Highway 401, and secondary routes connecting population centers. The region's economy depended on continuous electrical supply for heating, water pumping, and industrial operations. Forest cover consisted of mature deciduous and mixed stands with canopy heights, exceeding transmission line clearances in many corridors. January temperatures normally ranged from -15 to -5 degrees Celsius, with precipitation falling as snow. Ice storms occurred periodically, but historical records indicated events rarely exceeded 24 hours of continuous freezing rain. The design envelope for infrastructure assumed brief ice loading followed by wind or temperature change that would shed accumulated ice. No sustained multi-day freezing rain event had been recorded in modern engineering documentation for the region. On January 4, 1998, a persistent temperature inversion formed over the St. Lawrence River Valley. Surface temperatures remained at or slightly below 0 degrees Celsius. A warm air layer established itself between 800 and 1200 meters altitude, with temperatures reaching +4 to +6 degrees Celsius. Above this layer, air temperatures dropped below freezing. Precipitation falling from upper cold layers passed through the warm layer, melting into liquid droplets. These droplets remained liquid as they descended through the warm zone, but did not freeze during the brief passage through the thin, surface cold layer before striking ground-level objects. Upon contact with surfaces at or below 0 degrees Celsius, the supercooled water froze instantly. This temperature profile remained stationary due to a high-pressure system to the east and low-pressure system to the west, creating a persistent atmospheric configuration. Freezing rain began across the region on January 5. The inversion layer did not dissipate. Successive weather systems moved along the same track, each contributing additional precipitation through the identical temperature structure. Meteorological stations recorded continuous or near-continuous freezing rain from January 5 through January 9, with intermittent resumption through January 10. Total ice accretion in the most affected areas reached 75 to 100 millimeters radial thickness. This accumulation occurred incrementally over approximately 80 to 100 hours. The persistence of the inversion prevented any melting or natural shedding of ice. Ice accumulated uniformly on all exposed surfaces. Power line conductors, normally 15 to 35 millimeters in diameter, gained radial ice layers exceeding 50 millimeters in the most affected zones. A conductor with 50 millimeters of radial ice accretion increased its effective diameter by a factor of 4 to 6, and its weight by factors of 10 to 20. Transmission tower structural members accumulated ice on all sides, increasing cross-sectional area and wind resistance. Tree branches in forested corridors accumulated ice loads proportional to surface area. A mature deciduous tree with winter canopy could accumulate several tons of ice. Branch failure occurred first in smaller diameter limbs, then progressively in larger structural branches, as ice thickness increased beyond material strength limits. Fallen branches contact with power lines created short circuits and mechanical loading. Ice accumulation on distribution lines caused sagging between poles, reducing clearance and increasing mechanical stress on attachment hardware. Insulator strings accumulated ice, increasing weight and creating bridging paths for electrical leakage. Substation equipment exposed to freezing rain accumulated ice on bus bars, disconnect switches, and transformer bushings. Ice layers bonded directly to metal and ceramic surfaces, increasing weight and altering electrical properties. No mechanical shedding occurred because ambient temperatures remained below freezing and no wind event developed. Ice thickness increased monotonically throughout the precipitation period. Load stress on all structures increased continuously without relief. Transmission tower failures began on January 7. Towers supporting 735 kilovolt lines between Montreal and James Bay experienced structural collapse when ice loading exceeded design limits. A single tower failure caused mechanical overload propagation to adjacent towers through conductor tension. Sequential tower collapse occurred along specific line sections, with 5 towers in one corridor failing within hours. Each collapse severed high-voltage transmission capacity. Distribution pole failures occurred throughout affected areas as ice-loaded conductors exerted forces exceeding pole embedment strength and hardware ratings. Poles tilted, crossarms broke, and conductors dropped to ground level. Transformer failures resulted from ice bridging across insulation gaps, creating phase-to-phase or phase-to-ground faults. Automated protection systems isolated faulted sections, but the geographic extent of simultaneous faults exceeded system reconfiguration capacity. Substation equipment failed when ice accumulation caused insulator flashover or mechanical failure of support structures. The Hydro-Quebec transmission system lost major interconnection capacity on January 8. Over 1,000 transmission towers sustained damage or collapse in Quebec alone. Distribution system failures numbered in tens of thousands of individual component failures. Urban distribution networks experienced widespread outages as multiple feeder circuits failed simultaneously. The cascading nature of failures meant that repair of individual components did not restore service because parallel path capacity had also failed. By January 9, approximately 1.4 million customers in Quebec were without electrical service. An additional 230,000 customers in Ontario lost power. Outages in northern New York, Vermont, New Hampshire, and Maine affected several 100,000 additional customers. The duration of outages extended beyond typical restoration timelines because the scale of infrastructure damage required reconstruction rather than repair. Some areas remained without power for 4 weeks. Transportation networks became impassable as ice-loaded trees collapsed across roads. Autoroute 20 and other major routes closed for extended periods. Municipal water systems dependent on electrical pumping failed, eliminating water supply and sewage handling capacity. Communication networks degraded as battery backup systems in telephone switches and cell towers depleted. Emergency services faced access limitations due to road blockages and communication system degradation. The Canadian Forces deployed personnel for infrastructure security and population support. Temporary shelters opened in facilities with backup generation capacity. The prolonged nature of outages created compounding effects as fuel supplies for backup generators depleted and resupply routes remained blocked. Industrial facilities dependent on continuous power experienced equipment damage from uncontrolled shutdowns. Dairy operations lost production capacity. The simultaneous failure of multiple infrastructure systems across a wide geographic area exceeded mutual aid and emergency response capacity. Approximately 4 million people in the affected regions lost electrical service at some point during the event. Peak simultaneous outages reached 1.6 million customers. Outage duration exceeded 1 week for over 700,000 customers. Some rural areas remained without power for 3 to 4 weeks. The event caused 35 fatalities, primarily from hypothermia, carbon monoxide poisoning from improper generator or heating device use, and accidents during storm conditions. Over 900 people sustained injuries requiring medical treatment. Economic losses exceeded 5.4 billion Canadian dollars, including infrastructure damage, business interruption, agricultural losses, and emergency response costs. Approximately 130 transmission towers required replacement. Over 30,000 wooden utility poles were destroyed. Thousands of kilometers of distribution conductor required restringing. The dairy industry in Quebec lost an estimated 10 million liters of production. Maple syrup production equipment sustained damage affecting subsequent seasons. Insurance claims totaled approximately $1.4 billion. The scale of infrastructure damage required months of reconstruction work. Hydro-Quebec employed over 1,000 additional line workers from utilities across North America. The simultaneous nature of failures across multiple jurisdictions strained equipment inventories and skilled labor availability. Restoration prioritization focused on critical facilities, then main distribution feeders, then individual service restoration. Full electrical service restoration concluded in early February 1998, approximately 4 weeks after the initial outages. Infrastructure reconstruction continued for months. Hydro-Quebec implemented a network reliability improvement program involving tower reinforcement, increased conductor clearances, and enhanced ice loading design standards. Ontario Hydro revised design specifications for new infrastructure to account for ice accumulation events exceeding historical precedents. The event prompted revision of emergency response protocols and mutual aid agreements among utilities. The Meteorological Service of Canada and National Weather Service conducted detailed atmospheric analysis of the temperature inversion persistence. Engineering studies documented ice accumulation rates, structural failure modes, and load propagation mechanisms. The event established new reference standards for ice storm severity and infrastructure vulnerability. Academic and government research programs examined forest damage patterns, with an estimated 15 million cubic meters of timber damaged in Quebec. Insurance industry studies led to revised risk assessment models for infrastructure damage from ice loading. The event remains the largest ice storm disaster by infrastructure impact and economic loss in North American history. Official records documented ice accretion measurements, failure sequences, and restoration timelines that informed subsequent engineering standards across northeastern North America.